Hello everybody, my name is Pete Cook and this is the Hydrogen to Human series. In the next 10 films I'm going to tell you how a human being self-assembles from nothing more than clouds of hydrogen atoms. Now that's a big claim and it's a big story. But we do now have all the pieces to the story. Trouble is, we've got all the pieces mixed up. We can't see how they fit together. So part one, I'm going to lay out all the pieces of the puzzle that we've uncovered. And we know all these pieces are correct. They all work in their own domains. Biology, chemistry, meteorology, economics, social theory, physics, quantum physics, classical physics. We know they're all correct, but they don't fit together. So let's lay out the pieces of the jigsaw in chronological order so we can see the problems. And I'm going to use lots of very famous people who give us quotes, clues to the problem. Now I'm going to say the first time we really got to grips with science was Newton. Newton's laws were predictable. I could predict what was going to happen in the future. That's what human beings want to know, to give myself a safer future. I know what's going to happen. So that's what Newton brings in. An idea that one day we would be able to predict the future of all that we observe in the universe. But Newton's physics had a problem which is often overlooked. The predictability in Newton's physics only works at a very, very simple level. It just works for two bodies. As soon as you get to three, the Earth, the Sun, and the Moon, it suddenly changes into something completely different. And Newton's physics doesn't explain what we see in the solar system. If I looked inside the rings and belts of the solar system, what we see is completely chaotic behavior. In the asteroid belts, the asteroids don't have predictable behavior. They wander about all over the place. They're chaotic. So that's a problem. The reality that we see has chaotic behavior as well as predictable behavior. So let's move on in physics to the invention of the steam engine. This is where we really start to understand heat, thermodynamics. We get the second law of thermodynamics. Now, this is a very, very important law in physics. It's one of the overarching rules that we think governs the whole universe. But there's a bit missing. The second law of thermodynamics deals with energy. And the energy is always getting used up. It's always wearing out. It's always going from a state of order into more disorder. It's going towards equilibrium. So if I get a hot cup of coffee and just put it on the table, it seeks equilibrium. It spreads itself out. It goes from hot to cold until it's all just in a state, I can say, of everything's the same. It's found equilibrium. The molecules in this room don't all gather themselves together in one corner. They spread themselves out. They seek equilibrium until the pressure in the room is all balanced. Now we know that that law is true, but the reality that we observe doesn't seek equilibrium. It gathers itself together in clumps. Now we call this negative entropy. So I'm starting to see a contradiction. The first stars that form don't seek equilibrium. They gather themselves together and clump together. The reality that we observe is anything but a reality that just seeks equilibrium. I see incredible self-organization in both parts of physics. There are two parts of physics: quantum physics, atomic physics at the small scale, that self-assembles all the tiny bits, the atoms and molecules. And we don't see something that just self-assembles into an equilibrious blob, something like that. What we observe is that the tiny parts, the atoms and molecules, self-assemble into incredible symmetrical structures, self-organizing. Well, that's not entropy. Entropy is the correct description of what's happening to the energy, but the structure is not becoming more disordered. And if I look at gravitational structures, the other parts of physics, what we call relativity, just a relationship between matter and space, I don't see a solar system which seeks equilibrium and just spreads itself out. It self-organizes itself, builds itself into parts which turn into beautiful clockwork motions, which are so accurate our clocks can count them. So I've got some predictable parts. Inside the rings and belts I've got completely chaotic parts. And the whole thing is self-organizing. Even the chaotic parts are organized or all tidied up beautifully, put into rings and belts. Everything's in the right place. So if I look at the present view, we've got contradiction. I've got entropy, which correctly describes the energy in the universe. The reality we observe is completely different. Now we say negative entropy, but something cannot be negative unless it is positive. It has a positive partner. So something is really wrong. Now let's show how Brian Cox sees this. He knows there's a problem. Brian Cox is a very, very good physicist. So he's very well aware of this problem. So he says, notice there is nothing in the laws of nature that prevent entropy or this energy from decreasing. There's nothing that stops it from happening, but it can't provide the mechanism. Because if it's only seeking equilibrium, what I see in self-organization is the opposite of equilibrium. So that's a problem. So if you're looking at physics, the chances of the desert, this is the example that he uses, self-organizing itself into a sandcastle are zero. He says it's possible that the wind will build a sandcastle, but the chances are akin to tossing a coin billions of times and each one coming up heads. It's simply not going to happen. So we have to accept that the physics that we understand and know is true is not going to explain the self-organization we observe. Now let's read a bit more of what he says. If we try and explain it with physics, there must have been back here complete order that leads to disorder. But when I look at what we've got back here, this doesn't look very ordered. It starts back with a quark gluon soup, an equilibrium. Then that cools down into hydrogen. Well, hydrogen atoms are much more ordered than a quark gluon soup. So there seems to be a relationship with cooling down and more order. Something's not right. And this is what Brian Cox says. There is clearly something fascinating about the entropy of the early universe that we have yet to understand. So he says we don't understand. So there must have been a lot of order to begin with. Well, that's what the physics would say. The answer is that we don't know why the universe began with sufficient order in the bank. In the bank, a big bank of order. But a quark gluon soup? That doesn't make any sense. So there's the big problem in science. The reality that we observe doesn't fit with the description that we're trying to give using the laws of physics. Now, physics comes in two parts. The gravitational physics, we call relativity, and quantum mechanics. Now, there was a great hope when we came across quantum mechanics. This strange new kind of physics would give us an answer as to what life is. Erwin Schrödinger, who wrote down the Schrödinger equation, the wave equation, which describes how little units of energy behave relative to space, show that it's good physics once again. It's deterministic. I've got a little wave of energy sitting in space. But there was another problem. If you try and detect that wave, you can't. What you find is a little unit of energy suddenly appears, and you don't know where it's going to appear. It's gone from something which was deterministic into something which has a probability of appearing here or here. Now, it all works out, but I seem to have two different answers at the same time. And quantum physics did not answer the big question of how the little units, the atoms which I see making the elements, flip over into the very same atoms producing DNA and life. That's the big problem that Erwin Schrödinger wrote down in his book 1944. What is life? He hoped that quantum mechanics that builds the element would answer the question of how the elements, and only the elements, would start to explain this. That hasn't happened. And that was the great hope, that one day it would. So let's just read what Richard Feynman says about that hope. The next great awakening of human intellect may well produce a method of understanding the qualitative content of equations, what qualities they have, why things behave as they do, not just the quantities of the elements that we can measure, but how they behave, its qualities. How can elements suddenly start to behave as DNA? Today we cannot see whether Schrödinger's equation, quantum mechanics, contains frogs, musical components, or morality, or whether it does not. We cannot say whether something beyond it is needed or not. And so, we can all hold strong opinions either way. So here's a good book, and this is Roger Penrose, stating the same thing again. 6 decades later, after quantum mechanics, the question remains unanswered. Although biological processes are increasingly well understood at the biochemical level, from the point of view of fundamental physics, life remains deeply mysterious. Life seems an almost magical state of matter to physicists. Furthermore, its origins from non-living chemicals is not understood at all. So that's the big problem. It's not understood how we go from elements, which change into chemicals, molecules. I can't even take that step using physics, because the molecules don't just fall together like that. That's what the physics says. The only rules I've got in atomic physics are fall together, attract and repel. I don't have rules which self-organize into these beautiful molecules or self-organize into the Krebs cycle or DNA. So in reality, we see self-organization. Self-organization occurs in a variety of physical, chemical, biological, robotic, social, and cognitive systems. Well, that's pretty much everything. I've got to account for self-organization. I've got to account for chaotic behavior, which is a contradiction if my physics is always going to be predictable. Now I'm going to put an image of a chaotic pendulum. Think about it. These are physical parts with completely unpredictable behavior. That's contradiction if I've only got physics. So there's a missing part of physics here which can explain the reality which I see, in which I need some parts which are just predictable and simple physics if I drop a cannonball, some parts which are chaotic if a leaf falls off a tree. No computer on the earth can predict where it's going to land. A chaotic pendulum, and some parts which are self-organizing. So I see all that in the solar system, the chaos in the rings and belts, the predictability of the orbits, and the self-organization from dust into a clock. I see it at the atomic level, the atoms. I've got quantum uncertainty, I've got randomness, so I've got the predictability of the Schrödinger wave equation, and I've got the self-organization of molecules. So that's the problem laid out in part 1 of Hydrogen to Human. In part 2, I'm going to expose to you the missing part of physics and show you we've been staring at the answer for hundreds of years.